The absolute encoder has a coded disk. As an example, you see here the binary code. The construction of an absolute encoder is more complex compared to an incremental encoders, as they require a decoder. But the big advantage is that each angular position of the shaft can be read at any time, even after a power failure. That means there is no counter value to lose.
Absolute encoders have a unique code for each shaft position. In other words, every position of an absolute encoder is distinctive. The absolute encoder interprets a system of coded tracks to create position information where no two positions are identical. Advantages. First is the non-volatility of memory. An absolute encoder works as a non-volatile position verification device. True position is not lost if power is lost or the system moves while power is switched off. A continuous reading of position isn't needed, which is useful in applications such as satellite tracking antennas, where position verification is key. Absolute encoders also provide programming flexibility. By removing the need for system homing, the encoders can be controlled to give positioning programs based on setting up reference from point to point rather than from a home position. A microprocessor interface module allows for programming of various operating parameters, such as resolution. Safety is another benefit. In some applications where a loss of position could lead to operator injury or machine damage, an absolute encoder automatically provides position verification when the power is switched on. Absolute encoders also have good immunity to electrical noise. The device determines position by frequently reading a coded signal. Stray pulses from electrical noise will not build up, and accurate position is presented again on the next reading.
Alright, let's consider an optical shaft encoder example where we have a motor and we want to know the position of that motor somewhere around the 360 degrees. So we can use an optical shaft encoder for that, where we have a light source projecting through and a photosensor on the other side, and then some sort of encoded disk that we're going to use to indicate where we are around that disk. So let's consider two possibilities, one being the binary code for the positions and the other being gray codes for the positions. This is the table for decimal to a 421 coded binary decimal and the gray code equivalent. The 421 code would be similar to a binary coded decimal, which is how most people are familiar with binary numbers counting up from 000 to 001, 010, whilst the other code is the gray code, which you may not be familiar with, but it was named for Frank Gray, who patented its use for shaft encoders in 1953. The idea of the gray code is that it's a code having the property that only one bit at a time changes between codes during counting. So you'll notice here that as we count up or down in decimal, say between 0 and 1 or 1 and 2, then the code word for the gray code only changes by 1 bit position. So that includes between 7 and back to 0. Whereas the 3-bit binary code changes multiple bits at a time in certain circumstances. Then the question really is, does this special gray code property have any value for us when we're thinking about the shaft encoder? So if we look back carefully at this shaft encoder, we can see that as the light source and sensor is rotated relative to the encoder disk, from the 000 position, we notice that when it transitions between 000 and 001, that first bit could be either a 0 or a 1 when it's on the threshold. There is going to be a point at which enough light gets through that it's ambiguous as to whether it's a high or a low. Now, in this case, because it can either be 0, 0, 0 or 0, 0, 1, it's not really a problem. It means that the angle could only be out by a small fraction. However, as we continue to rotate it around and we get a nice clean reading 0, 0, 1, when the transition goes between 0, 0, 1 and 0, 1, 0, we notice now that there are 2 bits that are ambiguous. So it could be 0, and then the other 2 values could either be 0s or 1s. So therefore, there's 4 possible states there. Could be 0, 0, 0, 0, 0, 1, 0, 1, 0, or 0, 1, 1. Now, out of those 4 states, 2 are reasonable, that is, stepping between the values of 1 and 2. However, the other 2, 0, 0, 0 and 0, 1, 1, are definitely not what it is, and we don't want the encoder to mistakenly think that it's jumped backwards or that it's jumped over one of the segments. This would also be a problem if the system was powered up with the encoder in this state. It may be that if you think you're at 0, 0, 0, you want the wheel to move forwards, when in actual fact, if it was at 0, 1, 0 at 2, then you'd want it to move backwards. And so due to your mistaken encoder reading, you actually move the motor in the wrong direction. Grey code, on the other hand, whenever there's a transition, you'll notice that it's only 1 bit that's changing. So between 0 and 1, it's just that first bit that's changing.